In this lecture, we are going to finish off our work on second-order ODEs. Now, we've spent quite a bit of time looking at solution techniques. In the first lecture, I motivated the subject and I said, look, differential equations can be used to model physical phenomena. And the power in these modeling techniques is to be able to somewhat accurately predict future behavior and future states of the models under consideration. In this lecture, we're going to look at one particular kind of application, vibrating systems. Now, can I have a show of hands? Who's studied vibrating systems before? Okay, good. Some people may not have seen them. That's okay. So the nature of this lesson is quite introductory, quite basic. What's that? Oh, I do it in physics. Good. Okay, so I know it's a bit hard to see all the writing in here, so you might have to look at the page in front of you. This is like a spring mass type system. So you've got a mass attached to a spring, and the spring's attached to some, or fixed to some location. Essentially, what we're going to look at is the dynamics of setting that system, the mass, in motion. We're also going to look at how we can use differential equations to describe the dynamics. Okay, so let's just forget about the mass for a second. If you attach a spring to some fixed location, the spring will hang down a little bit. Then you attach a mass to it, the spring will hang down a little bit more. That position is known as the equilibrium position. And what we do is to set the mass in motion, we either pull it down or push it up and let it go. Okay, you can see in this graph here, we're going to take x as sort of above the equilibrium position. So what we would do is we push it and let it go. We would measure positive displacement in the upward direction. You can also measure it in the other way, in the other direction, as long as you're consistent. Okay, so suppose our mass is m, and we have a positive constant k, which is reflecting the stiffness of the spring. So if you have a large value of k, it means the spring's really stiff. X of t is going to measure the displacement from the equilibrium point of the mass at time t. Okay, so you can use Newton's second law, F equals ma, to come up with this basic model. Now, you may have seen this in other classes or even at school. This is a very basic second order ODE, and you can calculate the solution by looking at the characteristic equation, and the roots are complex, and you get the following solution x of t, where big A and big B are just constants that can be determined from the initial displacement and the initial velocity. Okay, well, what will the graph of this solution look like? Well, it's going to look something a little bit like this. Okay, you can see the spring is vibrating up and down, and this is just a basic representation. Now, is this an accurate model of what happens when you set a spring mass system in motion? No, not really. Why not? Yeah. this under this model, the spring would just keep bouncing up and down forever. That's not going to work. It's going to stop. Why is it going to stop? Well, air resistance, gravity. So this model is a very basic, somewhat unrealistic model for our spring mass system. What we're going to look at is damped vibrations. So the spring mass system has some sort of damping associated with it. And even in the previous model, I mean, there would be wind resistance or air resistance, right, of sort of damping in that model. So the damping force may be supplied by, say, air resistance or oil, something like this. And you can see there's three basic models here and some suggested plots of, say, the solution. Well, here the air resistance, so it would bobble up and down and, you know, eventually head towards the equilibrium position. With thick oil, it would not oscillate, but just sort of come back towards the equilibrium position. And then with water, you can see it actually comes back quite faster when compared with the thick oil. So there's some suggestions on what might happen. Okay. So what we're going to do now is try to set up and justify a more accurate model for these systems with these vibrating systems with damping. Okay, so m's the mass, k is the spring constant, large K means a stiff spring, and we introduce something called a damping constant. Okay, by this C. Now, a large value of C would mean that say the fluid involved, the oil, is very thick. Okay. Now, let's have a look at the forces at play that we'll consider. The restoring force of the spring is just assumed to be minus K times X. Now, this comes from an idea called Hooke's law, and it says that it's essentially proportional to the displacement X. Now, that's just one assumption. Hooke's law, who's heard of Hooke's law here? Can I have a show of hands? Yeah, that's one version of Hooke's law. Okay, that's a linear version. Anyone seen any non-linear versions of Hooke's law? Anyone? Where have you seen it? Yeah, good. So that's one force. We also assume the damping force is proportional to the velocity. Okay, now if you introduce Newton's second law there, you'll get the following. So essentially you just add these up. And if you rearrange, you'll get the following second order linear homogeneous dE with constant coefficients. So how do we solve it? Well, let's write down the characteristic equation given here. Remember, m, c, and k are all known numbers. Okay? So we can solve this just by, say, using the quadratic formula or some other method. What we're going to do now is look at different kinds of roots and see what kind of vibrations occur, if any. We're just going to look at the dynamics. Okay? So when you see R1 and R2, it's these sort of general forms. Okay. Essentially, it's all about c squared minus 4mk and the sign of c squared minus 4mk. So there's going to be some sort of relationship that we're going to look at between the mass, the spring constant, and the damping constant. Okay? All right, case 1, the so-called overdamped case. This is where everything inside this square root will be positive. In that case, you're going to get the characteristic equation is going to have real and unequal roots, and in particular, they're going to be negative, just because of the signs of M, C, and K. In that case, we know when the roots are real and unequal, the general solution is just a linear combo. Okay, so the R1 and the R2 there are just computed from here, but I didn't want to sort of write them all in there. Okay, so what does this look like then? Well, if I have a basic, just hand-drawn plot here, say X and T, this might be a graph of the displacement of my mass. It doesn't necessarily have to do that. It could do something like this. Could do something like that. Now, in both cases, I guess, you don't have oscillation. Okay, why? Well, to relate it back to the physical assumptions here, what does this mean? Well, it means that there's a strong damping force compared with a weak spring or a small mass. Okay? So you can see that the mass doesn't oscillate and it approaches the equilibrium, the sort of zero in the long term. Okay, the so-called critically damped case. This is when you have 0 in this square root. So that's just going to disappear. So in that case, the characteristic equation, your roots are real and repeated. Okay, so you know that in this case, when the roots are real and equal, you have the following solution. So to have a basic graph here, be something like this. Okay, again, there's no oscillation because the damping force is just enough to suppress them. And finally, the underdamped case. Okay, this is where you get complex roots, and this will be the form of your solution. So what does that mean? Well, essentially it means that your mass is just going to wobble up and down. Okay, so you can sort of sketch in these bounding functions. And you can see that, yes, you will get oscillations in this particular case, and the mass will settle down in the long run. Okay, so relating this back to the model, the oscillations will occur due to the weak damping force, for example, low viscosity oil, compared with a strong spring or a large mass. Okay, so dynamically speaking, the mass is just going to wobble up and down and return to the equilibrium position in the long run. So there are 3 basic cases when we have damping involved. The first one? Yep. This one? Yep. So in this case, no oscillations. I mean, it's a fairly badly drawn graph, but I hope you get the idea. In this case, even though it crosses the axis here, we wouldn't say that this was an oscillation. Okay, in this case, the spring returns very quickly back to, well, towards the equilibrium position, faster than this case. What's going to happen if it starts at 0? Yep. Okay, if it starts at 0, nothing's going to happen. Okay, you need to sort of put it in motion. Well, yeah. The system, if it starts at 0, it'll stay at 0, right? Unless you introduce some sort of external force, okay, which is the subject of the next part of this lecture. Forced vibrations. So we're going to speak about what happens and how to model the introduction of an external force or an external forcing function. So suppose that we introduce, say, an external force into the system. Okay, now I'm just going to use a periodic forcing function, but you can introduce other functions. Here A is a constant and big L is a constant. So in this case, what happens is our ordinary differential equation modelling our system becomes a little bit more difficult. Now note that 6 is just an inhomogeneous or a non-homogeneous problem, which we know how to solve by either the method of undetermined coefficients or the variation of parameters type method. But let's see what happens if we introduce this kind of periodic force function into our system. All right, the undamped case. So suppose I've got this external forcing function and I've got no damping. Well, this can be solved by standard methods. And if we introduce this notation omega, just being this square root, and omega is not equal to this L, then this is our homogeneous solution, and we can try, just using the method of undetermined coefficients, for a particular solution of this form. Okay, if you actually sit down and solve those and work them out in their general form, this is what's going to happen. So this is our solution. So what kinds, just have a look at that for a second. What kinds of vibrations are going to occur? Well, these two are just, you're just going to get some sort of curve that's periodic, repeating itself. And this might introduce something, but it's not going to introduce much because cosine is always between -1 and +1. So if you combine all those things into the bottom solution, your system is just going to sort of wobble up and down, right? That's for the case when this happens. Now, if you make that equal, then a big change happens. Okay? Your particular solution needs to be changed to something like this. And if you write out the general form of the solution just by adding the particular solution and the homogeneous solution, what is this term going to contribute? Well, sine isn't going to contribute much, but that t is. As t gets large and positive, t times sine of omega t, what's going to happen to that? Well, it's going to get large, right? And it's going to sort of oscillate, but it's going to get big as we oscillate. So to have a look at, to sort of give you some rough idea of what's happening with this system, it might look like this, right? Okay, so the magnitude of the displacement is growing and growing and growing. So what does that mean for our system? It's going to shake itself apart. Okay, so the external forcing function, in this case, combines with the natural frequencies, and it just sets up something that is going to go off and basically shake itself to destruction. Anyone know the term for this kind of behaviour? Resonance. Resonance. Okay. Although some people argue about what the meaning of resonance really is, but in a real basic setting, this is, I believe, an example of resonance. Okay. So these kinds of situations can cause all sorts of failures, and I'm sure you've studied things like the Tacoma Bridge and these sorts of things, right? You probably see them in first semester, right? But this is the mathematics of some of it. Now, another interesting example, who's heard of the Tacoma Bridge here? Can I have a show of hands? All right. Another example of resonance, resonance in important areas is in the space shuttle program. Okay, back in the 80s, the space shuttle program was shut down because one of the components was exhibiting resonance associated with the space shuttle. Now, unfortunately, every day the shuttle program was closed down, the US government was losing, I don't know, something like $500,000 a day. This is in the 80s. This is in the 1980s, right? So people investigated the matter, and they came up with this. They published it as a paper.